this is another important section. It's about modeling trigonomic functions when you're given a data. So here's a good example is tide. So let's just focus on this one and see what we can model with it. It's always good to do the examples in the book because the questions at the back often are based on the models in the book. So if we look at this, ignore October, that doesn't really matter. Well, it does in a way, maybe it's the 10th month, right? So October is the 10th month. But usually they're going to do a daily thing. So I tied approximately 10 meters at 2 p.m. and a low point of approximately 1.2 meters at 8:15 p.m. Now, if we think of this as a high-low sine curves rise to their high and they reach their low. The distance between the high and the low of any sine curve is half the period of the actual sine curve. Half the period from a high to a low. The distance between the top and the bottom, if you average them, will give you the axis. So let's look at that. The top is 10 meters, the bottom is 1.2. Let's add those together. We get 11.2. Let's divide that by 2. 11 divided by 2 is 5.5. 0.2 divided by 2 is 0.1. So we got 5.6, which means the axis is at y is equal to 5.6. We can now figure out the amplitude by taking the max and subtracting the axis. So the max is 10, and we subtract the axis of 5.6. And we get 4.4. So now we know the amplitude is 4.4. The other way to figure out amplitude is also using the max and min. You subtract them, 1.2, instead of adding them. You get 8.8, and you divide them by 2. So you would subtract max minus min divided by 2 gives you the amplitude. Max plus, let's see if we can do this, max plus min divided by 2 gives you the axis. Those are two important things to remember. Max plus min divided by 2 gives you the axis. Max minus min divided by 2 will give you the amplitude. You can also figure out amplitude, as I mentioned. Amplitude is equal to max minus the axis. And you can manipulate this formula any way you want. So therefore, amp plus axis is equal to max. Axis is equal to max minus amp. You know, all sorts of variations of all these formulas. But they're all important to know. So now we have two very important things. We know the axis at 5.6 and the amp is at 4.4. We also need to figure out the period. Well, it's max at 2 p.m. and it's min at 6:15, and so from 2 p.m. to 6:15 is 6 hours and 15 minutes, or 6 1/4. Which means that's half the amplitude, which means the actual amplitude is double that, which is 12.5. So 12.5 hours is the period. It's always going to be double between the max and the min along the x-axis. So now we have the period. We just don't know when it starts. So they're going to say a particular sailboat has a draft at 2 p.m. This means it can only move in waters that are at least 2 meters deep. The captain of the sailboat plans to exit the harbor at 6:30 p.m. So we're going to assume the tides are always like this for this specific period. And we're also we can start at any point. We can make the high tide the start. So for instance, if we're here, and we can make the high tide start at 6:20 if we want. But in reality, the start of the day is midnight, right? It's at the 00 hour. And then all the AM is to here. And then it's not till you get to over here on the other side that you get to 2 p.m. 2 p.m. and 6 p.m. So if we want our coast curve, let's say, to start there, the distance between 0, if that 0 is midnight, and 2 p.m. is 14 hours. So if we're going to switch our periods to 12.5 hours, we should subtract 14 in terms of a horizontal shift to the right so that the max occurs at 2 p.m. Let's see if all that works. So we also need a horizontal shift. If we assume the day starts at 00, we need a horizontal shift of minus 14, so that moves 14 to the right. And this assumes we're going to use a coast curve. If we used a sine curve, we might only add like a little bit less than that, but 14 worked good. So if I put this together, I can say y is equal to my amplitude, which is 4.4. I'm going to use a coast curve. I need to change, we need to figure out how to turn 2 pi into 12.5 hours, which is the new period. Well, as I've always said, you just divide by 2 pi and you multiply by 12.5. So you're going to be multiplying by 12.5 divided by 2 pi. But that's not how you actually change a period. You have to put the pi on top and divide by 12.5. You can also simplify this if you want. You can divide both by 2 and you get pi over this, or you can make it whole fractions and multiply it by 2 and you get 4 over 25, which probably makes more sense. 4 pi over 25 is going to create a period of that. So we're going to do 4 pi over 25, and then we're going to shift it minus 14, and then we have to add our axis. Our axis, as we've discovered, is 5.6. Now, this should produce, if I got it all right, a high tide at 2 p.m. And will also be able to tell me, I can either use the graphing calculator, or I can figure out the information that they want me to know. They want me to know when this graph is above 2 meters. Now, before I go to Desmos and cheat, let's figure out, and the ship wants to leave at 6:30, right? Let's figure out what happens between 2 and 6:30. So we know there's a high tide. Let's just pretend that this is 2 p.m. instead of the axis, the y-axis. We know it's at 10. And we know at 8:15, so that's 10, 2 p.m. comma 10. And we know that 8:15 p.m. we're going to hit a low. 8.25, which is 8 hours and 15 minutes is 8.25. And it's going to be the low of 1.2. If we look at this time here, it's going to go down, and halfway through it's going to hit the axis here. The axis halfway through between 2 and 8, 8.25 is 4.125. We add that to this, it's 6.125. So at 6.125, we're going to hit the axis, which we've determined was plus 5.6. I think we determined it. I've accidentally cut it off. So at 6.125, it should be 5.6. Somewhere between 6 and 825, it's going to be halfway between this distance. Between 6 and 825 is roughly an hour. So it's roughly 7, right? And halfway between 5.6 and a minimum of 1.2, if I take the halfway point of those two things, is I can subtract them. It's 4.4. It's roughly 2.4. So right away I can tell at 7 o'clock it's going to be 2.4 meters, and it's going to be fine. However, if you wanted to do this, let me see what I accidentally deleted there. If you wanted to do this algebraically, there we go, 5.6, you could. You're trying to discover when y is above 2 meters. So when is 4.4 times cos, and let's just call this angle for now, plus 5.6, equal or bigger than 2. Okay, well, our first thing to do is take 4.4 cos. Hope I got that amplitude right. Angle, and the angle gets transformed. We're just going to call it angle, is bigger than 2 minus 5.6, which is minus 3.6. Then I'm going to divide both sides by 4.4. And there's going to be two answers here. So when is the cos angle equal to a negative number? It's equal to a negative number in this quadrant and in this quadrant, which means we're talking about an acute angle, whatever acute angle I find, or it's going to give me a terminal angle. I have to figure out the acute angle and figure out the other terminal angle, because there's two possible answers. When this graph dips down below 2 and then back up, there's two possible answers. It's probably the first one that we're looking for, though. So now I need to figure out, well, when is cos angle equal to bigger or equal? Let's just call it equal to this. So we're going to take 3.6 and we're going to make it negative. And we're going to divide it by 4.4. And of course, we get a negative number that's less than 1. And we're going to go to trig, arc cosine, to find the answer of the angle. Now it's going to give us, we're going to work in degrees just for simplicity. And it's going to tell me the angle is this. which means the acute angle here is roughly, let's call that 145 just for simplicity's sake. I know it's not, and I don't like to round up this high, but let's call it 145. That means this acute angle here is 35, which means the other angle over here is 35 plus 180, or 215. So we're talking about 145 or 215 as the angle. Now we can bring in the transformations. So let's say when is 145, and now we have to translate 145 into degrees, into radians, and we have to do it by taking pi and dividing by 180. So it's really 145 over 180 pi equal to, that's how you transform. So it's really 145 pi over 180. There you go. That transforms it into pi radians equal to 4 pi divided by 25 times x minus 14. Well, I can see I have a bracket in here, so I have to get rid of this first. So I'm going to, how do you get rid of that? You multiply by the reciprocal to get rid of it. 25 over 4 pi, we'll get rid of it on both sides. So I'm going to multiply this left side by 25 over 4 pi, and that'll get rid of it on both sides. 25 divided by 4 pi is multiplying 145 pi over 180. Now, what do you know right away? The pi's just cancel. And we're just talking about a multiplication. 4 times 180 is 367.20. And I could do that. I think that's going to be times 100. That would be 5 zeros, so 7,250. I think it's going to be 36.25. 36.25. 36.25. So we're talking about 36.25 divided by 720. We're going to figure out what that is. And there's always a math error that's easily done in these. Divide by 720. And there we go. It's this. So we get this is equal to, and let's just call it 5 for simplicity's sake, is equal to x minus 14. When we add 14 beside to each side, we discover when x is equal to 19, which means if I look at hourly and I assume 12 is the start or 2 is the start, it looks like 17 hours. Now that doesn't quite look right. So I probably did a math error. Let's pull up Desmos first. And in Desmos, I'm going to do f of x is equal to 4 point, and we'll just see if we modeled it right first. 4.4 cos 4 pi divided by 25 times x minus 14, and then plus 5.6. So here's the model. It, of course, starts at midnight. We're looking at x is equal to, we determined it was x is equal to 2 p.m. is the max. So x 2 p.m. plus midnight is 14. So there's the max, so I got it. And then the minimum is going to be 8.25 later, 8 1/4 later, which is 14 plus, sorry, it's 6, 2 to 8 1/4 later, so it's 0.25, which is, there we go, I got it, which is 20.25. Should be the other low. So there we go, I got the other low. So we've modeled it correctly. 20.25 is the, oh, there we go, and that's why I came up with 17 in this, in the answer. I don't know why I went to, get out of this. See if I still have it here. I came up with, damn it, I think I had 19 in there. And that's why, it's because we've translated it to an hourly day. So I have it as x is equal to 19, I think it said, which is right there. So we can see it is indeed above that at that time. Now, the actual question asks, what does the actual question ask? If at 6:20 p.m. Well, 6:20 p.m. plus 12 is 18:20 p.m. Was it 20 or 30? 30. So that's 18.5. So we can see that the depth was indeed, in my quick analysis, deep enough to do it. And then if we look at y is equal to 2, we discover these points. 19, which is the one I came up with. There, I did do it correctly. And then it occurs later on in quadrant 3 at 21, which we could have figured out. But I did, after all that rounding, come up with 19. So 19, which is 2 to 19 is 7 p.m. is when the tide hits 2. And then over here at, what is that, minus 12, 9, almost 9:30 p.m., the tide comes back up high enough. This little zone here, the sailboat cannot leave the harbor. But at 6:20, not a problem. So my calculations were right. 19 told me that that was the time. I'd forgotten I converted it into a 24-hour clock when it would happen. Sometimes it's easier to start at midnight. It's often easier to start at midnight because if you make 2 the starting point, if you don't add this adjustment, then you have to remember that 0 here is 2 p.m. So now you know that's 2 p.m. and that's 6.25 hours later. The sail point cannot leave at 5.3. Now, obviously, modeling it is the way to go for quick and easy, but when you're in an exam, they're going to want you to do the algebra method that I just did. And it's always easier to replace this translation here with the word angle. And find the angle first, then figure out what 2 possible quadrants it's in, and then solve the translation of the angle, the x transformations. You always do that way. It's a lot. Your brain won't hurt as much. So you can see they do it again with temperature, average temperature in a season, moose population over months, owl population over months, combining the 2 to see if there's a connection between owl and mouse, to see if it looks like the owl population goes up as the mouse population goes down. As they eat all the mice, they starve, then the mice population grows back and forth. This is a good example of a sustainable system in nature, which is always achieves a balance when man doesn't interfere. Then they give you the same formulas I gave. They gave the overall transformation rules, which is A in front, K, which they tell you is actually 1 over K, X minus D, the minus is just to remind you to reverse everything, plus C, and then they do it again for cos. But they also tell you the rule for amplitude, max minus min divided by 2. They also tell you how to convert 2K radians. You multiply it by 2 pi and divide it by whatever period you want. So if you want 10 hours, that's what you put there. And then that just gives the horizontal. They just explain the translations. But this formula is valuable. The amplitude formula is valuable. And the axis formula I gave you that they don't give you is valuable. Then they just give you to go through a whole bunch of models. It's very good to practice these models. It's probably one of the most important sections in high school math and probably the most applicable to university. So we have a cos curve. It has an amplitude of 3, a period of 3 pi. The equation of the axis is 2. The horizontal shift is pi over 4. To the left, it's been applied. Write the equation as function. So it's a cosine curve. Let's figure out all the things. So the amplitude is 3. The axis is 2. So right away we get y is equal to 3 cos, and we don't know what happens here, plus 2. So that's really important. Then it says we want a radians of 3. So we want to go from 2 pi to 3 pi, which means we're going to multiply by 3 pi and divide by 2 pi. But of course we have to do the reverse, which is 2 pi divided by 3 pi, which means the pi's disappear, which means that's what we should do in front of the cos. Put the words 2/3. Then we should open the brackets, and they pretty much tell me we're moving pi over 4 radians to the left. So we have to do plus pi over 4 to counter the left, turn the left into the right. So that should give us the exact thing that they want. There's the amplitude, there's the axis, there's the translation right, and this is the only complicated part. You have to figure out how to turn 2 pi into 3. And as they tell you, you simply put 2 pi here over your new period. In this case, it's 3 pi, so the pi's are going to cancel out. That's why they told you k over whatever new period you want. Oh, sorry, they told you 2 pi over the period k, where they called the k the period that you want. So since our new period is 3 pi, the pi's cancel out, and that's what you get. That's how you'll get rid of 2 pi and turn it into 3 pi. Determine the value of the function in question. Oh, we've got to keep it around then. Determine the value of the function in question if x is equal to pi over half, 3 pi over 4, or an 11 pi over 4. So it's easy when they give you the angle, because then you just put it in as the angle. You don't have to keep the word angle in there. So the first one is pi over 2 plus pi over 4. Well, pi over 2 is 2 pi over 4. 2 pi over 4 plus 1 pi over 4 is 3 pi over 4 plus 2. Now you have to do your bracket first before you get out of it. So 2 times the 6 is 3. It's 6. 3 times the 4 is 12. That gets rid of this. This simplifies to pi over 2. And then we just have to find what the cos of that is, because this here is treated like a whole separate thing. This is treated like it's like a multiplication. Well, pi over 2 is 90 degrees. We know that x comma y, x is equal to the cos. And we know at 90 degrees, x is 0. So the cos of pi over 2 is 3 times 0 plus 2, which is 0 plus 2. So the value of y is 2 at that. The value of y is going to be 2 when x is pi over 2. So that's the first one. We can verify it by putting this into the example. Whenever they give you the angle, though, it's very simple. 2/3. The next angle they give us is 3 pi over 4 plus pi over 4 plus 2. 3 pi over 4 plus pi over 4 is 4 pi over 4, or simply pi. And don't forget the word cos that I have out here. 2/3 times pi is 2 pi over 3. And this is an interesting angle. 2 pi over 3 is almost a pi. We're in quadrant third and quadrant 3. And I could actually use my exact values here, because 2/3 over pi makes an acute angle of pi over 3. Pi over 3 is 60 degrees. So I would just have to pull up my exact values for 60 degrees. Exact values trig. And it helps if you use the pi version. Let's see, that one's not the pi version. And yeah, you can just pull up your triangles if you want. Right there we go. That's a good one. I bet you this turns black. Yeah, I knew it. Otherwise, you got to take a picture of it instead. Or you could just work with your exact triangles, but it's a lot easier just to pull up, once you've done the exact triangles, just to have an exact table. And now that we know, we just need to find cos of pi over 3, which is this. And then the cos is 1/2. However, we're in 2/3 pi where cos is negative. So we have to put a negative in front of this cos value. So that means 3 times negative 1/2 plus 2. 3 times negative 1/2 becomes negative 3.5. Plus 2 becomes plus 4 over 2. So we're looking at the answer of 1/2. So far we have an answer of 2.5 for 3/4. Now we're going to do the more complicated one, 11 pi over 6. So we're going to do 3 cos 2/3 x, and our x is 11 pi over 6 plus pi over 4 plus 2. The easiest conversion here is to 12, so this becomes 22 over 12, and this becomes 3 pi over 12. When I add them, I get 25 pi over 12. If I think about that a little bit, that's over 2 pi, isn't it? It goes all the way around twice, and it ends up with pi over 12. We don't have an exact value for pi over 12, so we're going to have to just multiply and see what we get. We get 2 pi over 36, which is pi over 18. We don't have an exact value on an exact value table. In quadrant 1, after we go all the way around, we're back in positive, so we just find cos of pi over 18. We use our trigonometry and we switch to radians. And we do pi, divide by 18. We find the cos of it. We get that, we multiply it by 3, and we add 2. And we get that interesting value, the only one that's unusual. Pardon me. So let's model this and see if this is accurate. Let's take our Desmos. Let's throw in our adjusted formula that we just found. F of x is equal to 3 cos 2/3 x plus 2/3 x plus pi over 4 plus 2. And now we're going to put in, here it is here, we're going to put in the angles. We're going to find out what happens when x is pi over 2 and see if we get 2. And we do. And we're going to figure out what happens when f of 3 pi over 4 and see if we get a half. And we do, 0.5. And then finally we're going to do 11 pi over 6. And oh, there we go. I got the wrong answer. I had 4.95. Let's see. 4.95. Let's see where I went wrong on that. And let's make this in radians. Over 2, maybe. It's still reading it in units, label, step, units. Yeah, we're in radians. So I'd have to divide that to figure it out. But keep in mind, I've gone all the way around once. Remember? And I came up with, I think I had 25, x is equal to 25 pi over 24, which is there. Yeah, so that's not correct either. So I'll have to go back and do that calculation again. That's the only one I didn't get right. So let's see what happened. What did I do wrong? So we're talking about the formula. It's always good to correct yourself on paper to get it ingrained. So 3 cos 2/3, and the angle we're using is 11 pi over 6 plus pi over 4. I probably did an addition wrong there. Plus 2. This becomes 12 if I multiply it by 3. This becomes 12 if I multiply it by 2. So I get 25 pi over 12. Oh yeah, okay, so 25 pi over 12. Let's see what that does for me. I had the wrong one here. That's over there. Saying 2.54. And actually that would be in here. I'd have to put all this in here. It doesn't matter. Let's just keep going. I multiply it by, let's just keep it in unadjusted. I have to multiply by that by 2. So that's what I did, is I adjusted the angle. I shouldn't have. 50 and multiply this by 3, 36. That's what I did. I should not have adjusted the angle until I did the multiplication. These are both divisible by 2. And that's about it. Now 25 over pi over 18, that's what I should have done, is 7 pi over 18, which is almost a half pi. It's almost 9. So it's not quite reaching it. So that's the acute angle that I've got to find. So there was my problem. But let's keep it as 25 pi over 18. 25 times pi, divide by 18. Hit the cos. There we go. Times 3 plus 2. That's the value. I should not have adjusted or simplified my angle until I did all the multiplications. And there's no need to find the acute, and it'll spit out the right angle. So if I look at this, 0.987, I look at my model, and I put it at x is equal to 11 pi over 6. I do indeed get that right answer. So it was just a simplification of the angle. That was a huge mistake I shouldn't have done. Don't simplify your angles needlessly. Okay, so that's number 2. Sketch a graph of the function. Question 1. Use your graph to estimate the x value between 0 and 2. Okay. So if this is my graph up here, my new pi is 3. Okay. And the cos curve usually starts up high here and goes down, comes up, and ends here at 2 pi. But we're going to end at 3 pi, which means the middle point is 1.5 pi, which means the halfway point here is half of that, which is 0.75 pi. which means the midpoint over here is 2.25 pi, or the 3/4 mark. The max value here is going to be 4 or 3, but the amplitude has been adjusted to 2. So the max value here is going to be 5, and the min value is going to be 2 minus 3 minus 1. The whole thing has been adjusted to the left pi over 4. So that's the hard part. So if I'm going to guess what happens between 0 and 2, and I look here, and I keep in mind that it's going to be over here, and x0, which is here, and 2, which is roughly here, estimate the x values in the domain when y is equal to 2.5 to 1 decimal place. Well, I'm going to use my graph for that. Boy, that's a tough one. Now, to do this, an easier way would be to take my coast values and apply the transformations. What are my 5 key coast values? Well, there's 0, 1, pi over 2, 0, pi, minus 1, 3 pi over 2, 0, and 2 pi, 1. My translations are multiply all my y values by 3 and add 2. So I get 3 plus 2, 5, 0 plus 2, 2, minus 3 plus 2, minus 1, 0 plus 2, 2, 3 plus 2, 5. And then it's to multiply all my x values by 2/3, or by 3 over 2 rather, and then subtract pi over 4. So this becomes 0, and this becomes minus pi over 4. This becomes, if I multiply it by 3 divided by 2, so that's 2 pi, 3 divided by 2, I'm going to get rid of the 2, and I'm going to get 3 pi, and if I subtract pi over 4, that's the same as 12 pi over 4, so it's 11 pi over 4. I hope I got that right. If I multiply this 3 and divide by 2, I get 3, 2. If I subtract pi over 4, it's the same as 6 over 4. Subtract pi over 4, I get 5 pi over 4. If this I multiply by 3 over 2, I get 9 over 2, which is the same as 18 over 4. And if I subtract a pi, I get 17 pi over 4. And this last one, if I multiply by 3 over 2, I get 6 over 2, which is 3, which is what I want. And then if I subtract, that's the same as 12 pi over 4. And if I subtract pi over 4, I get 11 pi over 4. This one might be wrong, because it's 3 pi over 2. If I multiply it by 3 over 2, I get 9 over 4. And then if I subtract a pi, I get 8 over 4, which is 2 pi. That's not right. That shouldn't be. Oh, no, that might be right. Let's go back and do this one as well, which is normally pi over 2. If I multiply by that by 3 and 2, I get 3 over 4. If I subtract a pi, I get pi over 2. Yeah, that's pi over 2. So that was wrong. The rest are probably right. So what happens between this spot and this spot? What are the estimates? Looks like it goes from pi over 2 to 2 pi. Oh, where y is equal to 2.5. That's interesting. So it hits the axis at this. Oh, it's from the beginning, from 0 to 2. So it starts up here and comes down here, somewhere in here. Now let's graph that and see what I'm doing wrong. Okay. Now they want me to restrict the domain between 0 and 2. I think it was between 0 and 2. I'll go back and see if it wasn't between 2 and 0. No, between 0 and 2. And they said smaller than, not equals. And where they say y is equal to 2.5. So they're saying between 0 and 2, where is it 2.5? Okay, yeah, 0 and 2 down here. And you'd have to say, what is 2 in terms of pi? 2 radians divided by pi is this many. What is 2 divided by pi? It's 0.6366, 0.6366 pi is roughly going to be at 2. So it would be, when is it 2.5? Graphically, that's tough to do. Like if we do the whole graph without the domain, it indeed starts there, indeed ends there. Pi 11 pi over 4. This 2/3 should have created a, oh yeah, that's 3 pi. Just doesn't look like it. Comes down, goes up. They want to know in this first 2. They use 2 radians, which is interesting. It's actually easier to figure out algebraically, because the question is, when is y 2.5 in the first thing? You do this instead of using the graph. Cos angle plus 2, subtract 2 from both sides, divide by 3. So that's the cos angle. Do arc cos to figure it out. This is the angle in radians. Let's call it 1.4. Now that's going to be equal to the translation. So you multiply by 3, you get 4.2. Divided by 2, you get 2.1. And then you just have to subtract pi over 4. And that's going to give you your x value of where, in radians, of where it happens. And it's telling me it's going to happen when x is equal to this. 1.31. Let's see if that's true. 1.32, they rounded up. Algebraically, it's actually a lot easier to figure out than graphically, because graphically you have to make your graph very accurate and just draw a line straight through. Did we even have our points right? I don't know. Get rid of that. Where's my axis? 2. Yeah, so it's saying between the peak and the axis. So that's one way to figure out. You can figure out between the peak and the axis will be 2. So since it's 2.5, it's somewhere before pi over 2. But I mean, graphically, you'd have to do a really accurate graph and draw your y line through it and just roughly see where it comes to. Much easier to do it algebraically, or more accurately. Sketch a graph, yeah. The height of a patch of a bicycle. So this is fairly important stuff. It's how to interpret words into models. So the height of a patch on a bicycle tire above the ground is a function of time as modeled on a sinusoidal curve. The height of the patch above the ground, so it's on a tire, it's just a little mark on the tire. Total distance it has traveled is modeled by another sinusoidal curve. Which of the following characteristics do the two sinusoidal curves share? Amplitude, period, equation of the axis. Well, that's weird, but let's use exact values. Let's pretend the tire has a 1 meter radius, which makes our life easier. And that would make it 2 meters above the ground when it's at the peak. Sorry, 2, not 1, not 3, 2, if it's a 1 meter radius. which means here's a tire, right? When the patch is down here, it's at 0. When the patch is up here, it's at 2. And the axis would be y is equal to 1. The amplitude would be 1 if the radius is 1. So we would have a sinusoidal curve if we start at the peak of this. Y is equal, we don't need 1, cos x plus 1. And that will give us a tire that starts when the thing is at the top. And that tells us the amplitude is 1 and the axis is 1. And if it's a multiplication of time, let's just say that that it takes 10 seconds to revolve. 10 seconds to revolve. If it takes 10 seconds to revolve, we're talking about 2 pi over 10, which is pi over 5. So it takes 10 seconds for the tire to go all the way around. The next sinusoidal curve is the function of the total distances it traveled. So let's find out how far that patch travels in 10 seconds. Well, it's going to go this, 2 pi times r, which is 1. It's going to travel 2 pi, so it's going to travel a period all the way around of 2 pi. So the distances traveled on a sinusoidal curve will be up off the ground and down and up again. So what do the two sinuses share? Well, they share amplitude. They don't share period. You could you could raise this above, because then it'll tell you. Then it'll tell you the tire is patches above the ground, then comes back down, and then goes back up. And if you start where you should, it'll look like that. However, this is a 10-second period, and this is also a 10-second period. So that means their period is also the same. Their axis is the same, and technically, if you want to use it as a, well, actually no, because it's going to go farther and farther and farther, right? So the period is not going to be the same, because it should just keep going further and further and further as it travels. The height, the total distances traveled, modeled by another sign. So the total distance it traveled, they'd have to stop at the peak. So I don't think that's going to have the same anything. That's an interesting question. I would say off the top of my head, axis and period. Actually, I don't even say axis. I'll just say period, because they're both 10 seconds. But the height is going to keep going, or distance is going to keep climbing the more the wheel spins. So I'm amazed it would be marked as a sinusoidal curve, unless they're talking about the function of the total distance it has traveled above the ground as it approaches the ground, which is probably what they actually meant. That's just a poorly worded question. Okay, this is going to be a more model. We'll be able to model it a little bit easier. So he's doing a sparkler in a circular motion at a constant speed. The sparkler is moving in a perpendicular to the ground. So the kid's essentially going whee. Function of time can be modeled by a sine curve. At t0, the sparkler is at its highest point. So that almost tells you right away at t0, we should be using a cosine curve. We should also assume he never goes past the ground. The height of the tip of the sparkler function at time 0. Sinusoidal function. At t0, the sparkler is at its highest point. Now, he's not going to hit the ground with that, so we should add a certain distance. What does the period of the sinusoid represent in this situation? One full circular motion. One full circular motion. What does the equation of the axis of the sinusoid represent in this situation? The axis of the circle that he's spinning around. If no horizontal translations are required to model a system, should a sine or cosine function be used? Cosine, because cosine starts at a max value, and they say the sparkler starts at time 0, at the highest point, if we're not going to do a horizontal translation. Now, ideally, you do not want to hit the ground at the bottom, so you should add a vertical translation. Otherwise, the sparkler would go out. 6. to test the resistance of a new product to temperature change. The product is placed in a controlled environment. The temperature of this environment as a function of time can be described as a sine curve. The maximum temperature is 120, the min's minus 60, and the temperature at T0 is equal to 30, so there's an adjustment. So right away, we can do these equations. Max plus min divided by 2 will give me my axis. So we're talking 120 plus minus 60, which becomes plus minus 60 becomes minus 60, which is 60 divided by 2, which is 30. So my axis is 30 Celsius. The max, or the amplitude, is going to be equal to max minus my axis, which is 90. Just using a sine curve to start. Let's use a cos curve because it starts at max. It takes 12 hours of temperature change from the max to the min. Okay, that's important. But we're not going to translate this just yet. We're going to just start with the basic sine curve. So we're going to do 90 sine, we don't know what's going on in here, plus 30. Now right away they tell me between the max and the min takes 12 hours. Well, the max to the min is half the period. So that means the period is 24 hours. To change the 2 pi into 24, we take 2 pi and divide by 24, or pi over 12, which means right here we're putting the pi over 12. X. Now here's the problem, where it starts. If we look at what we've done here, we have started a sine curve, and it will be at 0 time. It will be at the axis, 30. It will rise to 120 and come back down to 30 and go back down as far as minus 60 and back up to 0. They tell me if the temperature is initially increasing, so it's got to be on the way up, and the temperature times 0 is 30, we have it as 0. That means we've got to take a sine curve and shift it to the left by 30 degrees. It's because it's going to hit 30, or it's going to hit 30 degrees at 0. So times 0, it's going to hit 30. And we're, oh yeah, no, we got it already, because the axis is at 30. So boom, and it's on the way up. If the temperature is initially increasing, what is the equation of sine function that describes the temperature of the environment? This is it. So let's see if we got it. All right, now we got to just model it a little bit better. We've got to put in the axis, and we've got to be able to see it. So this is going to happen over 24, so that's fine. This is going to go all the way down from minus 60 to 120, like that. And we'll just zoom out a bit. So sure enough, we start at 30. We hit a max, 6 hours in at 120, back down to 30, back down to minus 60, and 24 hours we're back to 30. Between the max and the min is 12 hours. As described, let's make sure we got it. Temperature times 0 is 30, which we have. So we got it. There's no horizontal adjustment. Had they had the temperature at a different thing, let's say the temperature in the beginning was 50, we'd have to figure out the distance between 50 degrees in X and 30 degrees and how much to shift it to the right. Like you'd have to do this. Let's find X is equal to, or Y is equal to 50. We'd have to subtract whatever that X value is. 0.856. So we'd have to say, we'll shift left, So that's if you wanted to start it, see, at 50 degrees, roughly. You'd have to figure out how much X value I have to shift to get to 50, which means you'd have to start at this. You'd have to figure out the X value for 50 degrees by punching in radians of 50 degrees. Or sorry, you'd have to put 50 over here. And then you'd have to figure out your X, and then you'd have to use that as a translation. But in this case, they've simplified it for us. So this one, a person who's listening to a siren reported that the frequency of the sound fluctuated with time measured in seconds. So our period's going to be in seconds. The minimum frequency heard was 500 and the max was 1000. What's the amplitude of that? Max plus min divided by 2. That's 1500 hertz divided by 2, which is 750 hertz. So the axis is 750 hertz. Now I can still use the max min to figure out the amplitude because it's going to be max minus min, which is 500 divided by 2, 250. I could also do that by taking the max and minus the axis and also get 250. That means the amplitude is 250. The max of frequency occurs at time is equal to 0, and then again at time is equal to 15. The distance between two maxes is always the period. So that means we're talking about a period of 15 seconds. To change an amplitude into 15 seconds, we have to do 2 pi over 15. And since it starts at a max, we'll use a cos curve, and it should be fine. So that means we're talking of this. Y is equal to 250 cos 2 pi over 15, which should convert it to a 15 seconds. Cos x, there's no horizontal translation, like that, plus 750. And we'll just do it. And then we have to make all the adjustments for the new thing. It's now y is equal to 750. And we have to change it enough to see it. So we're talking a 15 seconds. So we're going to switch to this. And we're talking 15 seconds. So we're going to stop every second. We're going to go up to about 22. And this is going to go from 500 to 1,000, 1,500. And look at that. We've got too many things here. We're going to go from 0 to about 15. It looks like I got the period wrong. Oh, not step of 1. Step of like... yeah, step of 1. So did I type something in wrong? That should get rid of that. That should turn it into 15. So we should have a 15-second period. We have to get rid of any labels. From 0 to 15. That period is not right. That period is also not right. Oh, there you go. Stupid. So if we go back and change that to steps of 1, and this goes from 500 to 1,500, and we just look at the period, and it goes from 0 to 2 pi, so it didn't translate it at all for me because it's got some sort of snafu in here. Oh, sorry, stupid. There we go. Whew. So we can see it goes from peak to peak in 15 seconds, goes to the minimum at 7.5, and the middle's at 750. Sorry about that. Brain fart. So that's it. Okay, a game show contestant spins a wheel. that is located on a plane perpendicular to the floor. He grabs the only red peg on the circumference of the wheel, which is 1.5 meters above the floor. So we don't know if it's at the bottom here or in the middle or wherever. We just know it's 1.5 meters at the floor. It grabs the only red peg on the circumference of the wheel. That's all we know. We just know it's 1.5 meters above the floor. And pushes it downwards. So he's going this way. Or let's say it's over here and he's pushing it this way. Yeah, let's go with that way. The red peg reaches a minimum height of 0.25. So that means it does reach a distance off the floor of 0.25. And then above the floor and a maximum height of 2.75. So right away we can see the axis. It's 2.75 plus 0.25 divided by 2, which is 1.5. We also see the amplitude, which is 2.75 minus 1.5, which is 1.25. Sketch out 2 cycles of the graph that represents the height of the red peg above the floor as a function of the total distance it moved, and then determine the equation of the sine function that describes the graph. So at 1.5, it just so happens that 1.5 red peg we've discovered is at the middle. Because we've discovered the axis is 1.5. He's pulling downwards, so it's going to go down and then up. Now, as a sine, since sines usually go up and then down, this one's going down and then up, which means it's going to have a reflection in the x-axis, which means it's going to have a negative number in front. Since we've determined that the amplitude is 1.25, and we've also determined the axis is 1.5, we've got the 2 y transformations, but we have to put a negative here, so the sine curve goes down. Now, we have to figure out, sketch 2 cycles like that. He grabs the only peg of the floor, pushes it downward. The red peg reaches a minus 0.25 above the floor and minimum above the floor. Sketch 2 cycles of the graph that represent the height of the peg as a function of total distance moved. And then determine the equation of the sine function that describes the graph. So, represents the height of the red peg above the floor as a function of the total distance it moved. I imagine it's the distance from the floor up and down. Now notice that they do not give us any reference of time, like it takes 10 seconds or anything like that. So really, we're just talking about sine x. We're just saying it's going to travel that distance above the floor over and over and over again. So let's see if that comes close to describing it. 1.25 sine x, and it's plus 1.5. And then we're going to make this go from 0 to 4 pi in steps of pi over a quarter, and the y-axis is going from 0 to, let's say, 3. And there we go, and we're going to make it 2 cycles, which is like this. 0 smaller equal x, smaller equal to 4 pi. And that should be it. Now, don't forget we have to have a negative in front so that the wheel heads downwards first. So here's the wheel at 1.5. It goes down all the way to 0.25 and up all the way to 2.75 and then down and then up and then down. And that's 2 cycles of the wheel. Because they did not give us any time reference or any notion of the time, I think you just have to stick with 2 pi as the period, because there's 2 pi is any period of or cycle of any wheel. And they don't really give us anything other than that. Now I'm going to just pause and check the answer. Okay, so they have it as 4/5. So they've changed the thing to 4/5. So I think what they're implying is we have to adjust the 1.25 radius into there. Yeah, and here's what they're doing. Because the amplitude or radius of this circle is 1.25, they're saying the distance traveled isn't 2 pi. It's going to be 2 pi times the radius, which is 1.25. 2 pi times 2 times 1.25 is 1.25 times 2 is 2.5. And how you get 2.5 is 5 divided by 2. I don't know where they get 5 over 4. Let's see. Let's try that again. 1.25 times 2 is going to make a distance of 2.5 pi, which is the distance traveled instead of the normal 2 pi. if I take that 0.5 and look at 2 pi like this and say, okay, well, the 0.5 is the same as 2 over 1, which is, oh yeah, it's not, to turn 2 into 2.5, you have to multiply it by 1.25. If I multiply this by 5 up top, so this is over 1, right? So if I multiply this by 5 to get it to 5, if I multiply it by 4, this becomes 5, and this becomes 4. So that's where they're getting it from. 1.25 is the same as 5 over 4. However, to change 2 pi into 1.25, I don't multiply it by 5 over 4. I multiply it by 4 over 5. So they're essentially turning 1.25 into the fraction 4.5. So there is a period adjustment because the radius is not 1 as a unit circle. It's 1.25. 1.25 is the same as the fraction 5 over 4. However, in front of x, we would represent that as 4 over 5. And that would adjust the circle. So let's see if that's what happens. Oops. Let's see. Okay, this negative times the sine. There we go. Let's see. And now the period is now 5 over 4. So the period is now 10 pi over 4, which is 5 pi over 2. So we should go from twice that, which is 10 pi over 2. And 10 pi over 2 is 5 pi. So there we go. That's 2 full cycles down to here and down to here. So yes, it's going to be slightly longer in distance because of that 1.25 radius, which would normally be represented as 5 over 4. However, you have to flip it for your x values. So essentially that 1.25 becomes 1 over 1.25 to get the proper values. And that is the same as 4 over 5. And then you have to adjust, you have to figure out your new period to be 2 periods. That would be 4 over 5 times 2 pi. And that becomes 8 pi over 5. Or sorry, it becomes 5 over 4 times 2 pi. So 5 times 2 pi becomes 10 pi. And then the 4 is there. And you have to divide both. Well, let's try that again. We multiply 5 times 2 pi, we get 10 pi over 4, which becomes 5 pi over 2. And when we multiply by that 2 cycles, we're talking about 5 pi, which is why you have to make this over here 5 pi to hit 2 cycles. Because 1 cycle is 5 pi over 2. So there's 1 cycle. And there you go. That's how you do it. You have to adjust whatever the radius is for the new period, and you have to express it as a fraction and then flip it upside down. So here we can see a Ferris wheel question. They're very easy. And it always helps if you visualize the Ferris wheel. And it's saying it had a diameter of 56. Well, diameter of 56 won't tell you the amplitude, but half that will, which is 25 plus 3, 28. So that tells you the radius, which will also be the amplitude of the Ferris wheel. One revolution took 2.5 minutes, so that's going to tell us the period. Riders would see Niagara Falls if they were higher than 50 above the ground. Sketch 3 cycles of the graph to represent the height of the rider above the ground as a function of time. The rider gets on at a height of 0.5 meters at time 0. So let's say he gets on here, and it's 0.5 meters off the ground. We discover that from here to the center is actually 28.5, which means our axis is at y is equal to 28.5, and our amplitude is 28. So right away, since we're getting on at the bottom, if we think about a cos curve, you get on at the top. So we want to reverse a cos curve and get on at the bottom and go up. And then they want how many? 3 cycles. Okay, and then they want the time intervals that when they see my Niagara Falls. So far we have this. Y is equal to 28, and we got to reflect it down, so negative 28 cos. We don't know the translation here, but we know that it's 28.5 meters. The center of the axis is 28.5 meters off the ground because it's radius plus that 0.5 at the beginning. How do you turn 2 pi into 2.5 minutes? So if this is in minutes, then we just leave it at 2.5, which means we take 2.5, we do 2 pi, we divide by 2 pi, and then we multiply by 0.25. However, we got to flip that, so the fraction we actually put in front is 2 pi over 2.5. If we double both of them to keep it a whole fraction, we get 4 over 5. So we're talking about putting 4 pi over 5 to change this. Now, there's the formula, but we cannot figure out how many times this hits 50 degrees, or sorry, a height of 50. And the height on this is going to be over here. But first, let's see if we've got our graph correct. And then we want it for 2 cycles, which is from 0 and smaller or equal to x, and 3 times 3 cycles. 3 cycles of 2.5 are 7.5. And then we're just going to make it visually more useful. There we go. And here we go. You get on at the bottom. I'm going to just change the things to like 1, steps of 1. You get on at the bottom. You reach a height. Here, you reach a bottom at the 2.5 minutes. Go up to the top, bottom, and top. Now, if we wanted to confirm when are we reaching a height of 50, that's what we would do. But what we're going to hunt for is these first 2 points without using the graphing technology. And notice it hits the point on the way up and on the way down, and then again 2.5 minutes later. We just add a period to these 2 points and then add 2 periods to get these 2 points. So all we have to do is find these 2 points. So we're trying to reach 50. So we're going to do this first. 50 is equal to minus 28 cos, and we're just going to call it angle, plus 28.5. First thing we do is subtract 28.5 from both sides, and we get 22 or 21.5 on this one. And then we got to divide both sides by negative 28, so you get negative 2.5 by 28 is equal to the cos of our angle. Where is this? Where is cos negative? In quadrants 2 and 3. So the first one we're going to find is almost always going to be quadrant 2. So we have to first, let's keep it in radians. We're going to do 21.5 negative divided by 28. And then we're going to put it in radians. And we're going to hit second arc cos. And we're going to discover this. I'm going to keep it as many this. This is how many radians. And if we wanted to put that in pi radians, we would divide that by pi to see if it's anything like a whole fraction. It's 0.77, so it's like 77.86 over 100. So it's not going to be a fraction. And if you turn it upside down, you can see that's probably not going to be a fraction. So really, we're going to work in radians. Well, when we go around an angle, 2.44 radians, the whole distance here is pi radians, which is 3.14. So we're definitely talking about this distance. If we want to figure out the acute angle, We're going to just keep that somewhere. We're going to keep all this upstairs, so we don't need the information anymore. If we're going to keep the acute angle, we're going to take pi, and we're going to subtract that 2.44. And then we're going to take pi and we're going to add whatever that was to find the quadrant 3 angle. This 2.44 is, yep. And this will find our quadrant 3, our quadrant 3 value. This will find our quadrant 2 value. Well, we've already found our quadrant 2 value. It's 2.44. So let's find our quadrant 3 value. So we're going to take the 2.44 that we had. I wonder if I still have it in the paste. Yeah, I do. We're going to subtract pi from it, even though it's pi minus it, and we're just going to make it positive. And then we're going to add that to pi. And this is our second quadrant 3 value. So we're talking about these 2 radians. Let me just get rid of the last bits. 2.444. Now we take our 4 pi over this is going to be equal to our first angle. 2.446286, let's say. We have to multiply it by 5 and divide it by 4 pi to get our value. Let me put this in memory. No, I don't have it. Okay, we're going to take our 2.44. And we're going to multiply it by 5. And we're going to divide it by open brackets. 2 times pi, close brackets, equals. And we get this in x. So it's at 1.9, call it 1.947 minutes on the way up. It's the first one. And then plus 2.5 and plus 2.5 for the other two. And then this for this 3.83, we have to multiply this 3.836899 times 5. Oh, it's divided by 4 pi. Damn it. Let's try that again. So this is incorrect. This one here. We have to take 2.44, 62, 85, 77157, whatever. We have to multiply that by 5. We have to divide it by open brackets, 4 times pi, close brackets, equals. And we get this. It's actually this many minutes. Let's just call it 0.97 minutes on the way up, plus 2.5, plus 2.5. So I'm roughly 1 minute, really. And then to figure this other one, 3.83, we have to multiply it by 5 and divide it by open brackets, 4 times pi, close brackets, equals. This happens at 1.52 minutes. And now if you want to figure out, let's get rid of all these things now. If you want to figure out where it happens, let's just call it 1.5 minutes, and even 1 minute would be good. If you want to figure out where the next 2 points, well, we add 2.5 to, let's just say 1. It's going to happen at 3.5. Not quite. It's going to actually happen at 3.497 or something like that. I mean, I could just add it if we wanted to. Let's just call it 1, though. 3.5. It's not going to be 1, just so you know. And then plus 5, 6. It's going to happen at 6. And the other one's going to happen at 1.5, 4, and 7.5. And so now we're going to go back and see if that's true. So sure enough, 0.973 is when it's on the way up, 1.527 on the way down, and then you add 2.5 to it each time to get the other 2 points. So you can see that method works. always to find future periods, you just add a period to whatever you found in the first two. Just remember there's always two angles, one on the way up, one on the way down.